Welcome back to Supervised Learning. I'm Ludwig Botmann, and in this video I will tell you about covariance functions for Gaussian processes. Covariance functions can be used to control the functional form of random draws from a Gaussian process, and we will see some examples of common covariance functions like the squared exponential and the Matérn. If you think back to the introductory video on Gaussian process, hopefully you recall the marginalization property of Gaussian processes. We said that the Gaussian process is defined via this marginalization property. So that is that for any set of points in the feature space, the marginal distribution is a Gaussian distribution with some mean vector and some covariance function. The mean vector can be computed by some mean function, and the covariance matrix, and that's what we will speak about in this video, the covariance matrix can be computed by some covariance function, lowercase k in this sense, in this case. So we have this covariance or kernel function that defines the covariance kernel or gram matrix. And as in support vector machines as well, we want K to be a valid covariance matrix, which means it should be positive semi-definite for any choice of inputs x. And this means that also the functions, the kernel functions K, should be positive semi-definite functions so that we get valid covariance matrices. You can also go back to the chapter on support vector machines where we discuss more on kernels. But now we want to get some grasp on what these covariance functions do. We will first see an example of a stationary covariance functions. Later we'll have different characteristics of covariance functions, but stationarity is the first one we look at. And this is very much related to the concept of spatial correlation. So let's say we have two data points in the feature space which are close in the feature space by some measure, let's say Euclidean metric. Then we want to have the function outputs also to be close, right? So the only thing we have to be careful about here is that f of x and f of x tilde, these are random variables. So we can't really say they are close before observing them, but we can say they should be more correlated. The closeness of 2 points in the feature space is measured just by the distance, so just x minus x tilde. And we call kernel function stationary if and only if it is a function of this difference. So if we can write the kernel function as k of d, then we say it's a stationary function. Intuition-wise, this means that a stationary k implies functions that do not depend on where the points lie in input space, but only on their difference. But I think it's easier to see later in examples what this means. But from the formula, it just means if you can write the kernel function as a function of d, then it's a stationary function. Okay, let's have a look at this example here. So we have a Gaussian process with this kernel function. We will see later what this kernel function is called. For now we just accept it as is, and as you can see it's clearly a function of d, right? So we have d in here and the x and x tilde only enter this formula via d. Yes, via d. So yeah, formula wise this is definitely a stationary function. Okay, so it is a stationary function, but here in this example it's not the main focus that the function is stationary. It is stationary, but the focus of this example is more to understand what these kernel functions and these covariance functions do. Later we'll speak more about what stationary exactly means. So we have these 2 points here, 3 and 2.5, x1 and x2. And if we want to get the correlation between those two, we have to look at the distance, of course, of those two. So we just take x1 minus x2, right? So then we have d1 is 0.5. And here at 0.5, we can look at the correlation of these two, of the y values that correspond to these two x values, because here we have a plot of the kernel function. So this is a pretty high correlation, right? The highest correlation would be 1. So here, yes, they are almost perfectly correlated. So if we now draw a random point from this distribution, this should be rather close to the original y1, right? So it should not be very far away here, and that's also not the case. So y1 and y2 are rather close in f space, which makes sense because they were close in the x space too. Okay, let's now say we have a new data point in the feature space x3, which is further away from these other two data points. And if we then look at the difference and at the k value at this difference point, we have a rather low correlation of y values in the y space with either of the other two values. So y3 could be further away from this point, right? It can be higher, it can be lower. We can't say anything about direction. We just say, okay, it's not that much correlated, so basically anything can happen. Okay. So I already teased that we have some different properties of covariance functions. Stationarity is the first property, and I want to explain this a little bit more in detail here. We already said that it's stationary if we can write the covariance function as function of the difference of x and x tilde, and that remains correct. This means also that we have a translation invariance in the feature space, which means that if I compute the kernel function for two points x and x plus d, which just have the difference d, then this should be the same as the kernel of 0 and d, right? So we have this invariance to translations. And yeah, don't worry too much about notation here. Sometimes we use k with the argument d, with just one argument d, the difference. Sometimes we use k with two arguments. If we use it with two arguments, of course, the two different points in the feature space. If it's one argument, then in this case it's the difference between those 2 points. Okay. Now, let's try to understand stationarity visually a little bit. So we are operating in R, so x and x tilde are just real numbers, and we plot the contour lines of this kernel function here. So let's start on the left-hand side. This is a stationary kernel, and if you look at this image, what you observe is that we have a lot of diagonal lines, right, which are parallel to each other. And this exactly characterizes a stationary kernel, because if you try to find those contour lines, you do exactly this. You take the difference of those two things here. So this middle contour line here is related to d is exactly 0, because x and x tilde have the same value. And if I set translation invariance, this means that the covariance is the same on all the points on this line here, right? It doesn't matter where x and x tilde are. It just matters that their difference is 0. So if the difference is 0, the exact location doesn't matter, but this does not only hold for the difference of 0, but for any other difference too. So if we take something like this here, the difference will be, I don't know, 2 more or less, right? And if I move on the difference point here, all the covariance values will have the same value as well. And the same if I go up here, there we are then in the negative half space of this. So if all these, or if we have a stationary kernel, then this contour set must be the same for these and that, just translated by this difference here. So, and more important, perhaps the second point here, the contour lines are parallel to the diagonal. On the right hand side, you don't see this, so there are no such parallel lines here in that plot of that kernel, so this is not a stationary kernel. Okay, that's just for one dimension. In 2 dimensions it gets a little bit more complicated visually, but you can always go with the definition of that you can write the kernel as a function of the difference. The second important property that a covariance function can have is isotropy. A kernel is isotropic if we can write it not only as a function of the difference of 2 points, but as a function of the length of this difference, so as a function of the distance of the 2 points. This is notationally r, which reminds us of a radius of a circle, right? And we'll see later why that makes a little bit sense. So if this is the case, then we have rotation invariance. Okay, so for stationary kernels we have translation invariance. For isotropic kernels we have rotation invariance. And one important thing also is that isotropy implies stationarity. So every isotropic kernel is also a stationary kernel. And another slide notational abuse, now we have k of r. So it's also a one-argumented k function, but this time it's just the scalar distance between the 2 points. Okay, let's see another example here. On the left-hand side we have an isotropic and stationary kernel. The difference to the plot on the last slide is that now we are operating in R2. So the x and the y-axis here are no longer just x and x tilde, but we are looking already at the difference components. So the first thing is the difference in the x component. The second axis is the difference in the second component. And isotropy means that if we would draw these contour lines here, that these contour lines would just be circles around 0, which exactly mirrors this rotation invariance, right? So it doesn't matter where exactly the points are, it only matters how far they are away from each other, right? And it also does matter in which direction they are located to each other, which can matter for a purely stationary kernel, which is not isotropic, but for an isotropic and stationary kernel it doesn't matter. And on the right-hand side, you see an example of an anisotropic but stationary kernel. It is stationary. Or why is it stationary? Perhaps think about that for a second. It is stationary because we can actually draw this plot here, right? It's a plot of the difference. We are plotting D1 and D2, and as we can do that plot, it's clearly a stationary kernel. But it is not isotropic because these lines here are not circles, but they are ellipses, right? So in one dimension, in this dimension, we have more variation than on that dimension. So it's not rotation invariant because it matters where exactly I would be on a circle. Or if I would draw a circle here, perhaps that's a better explanation. If I move around that circle, I end up in different covariance values, right? Okay, that's isotropy. The third property that the covariance function can have is that it is a dot product. We don't have an example here for now, but later there will be examples on dot product kernels as well, which is defined as this thing here. So if I can write it as a function of a dot product, a scalar product between the 2 points, then it's a dot product covariance function. Okay, so far on the properties. Now let's have a look on some examples of covariance kernels. The first and, well, perhaps simplest and most useless kernel is a constant kernel. We just say that the covariance between 2 data points is constant. So wherever you are, wherever those 2 data points are, it's just a constant value. Interestingly, and it's at first sight not that clear why that should be the case, a constant kernel implies constant function priors. So if I draw from a Gaussian process with such a constant kernel, then all draws from this Gaussian process as you can see here, are constant functions. This seems okayish because why not, but if you think more about that, it gets more complicated. I don't really want to speak more about this here. We can do this another time, but keep that in mind. So there is this relation between the type of the kernel function and the type of the functions that you draw from a Gaussian process if you use that kernel function as a covariance function. Yeah, but that's my comment on this for now. Okay, this kernel is not that useful, it's just a constant kernel. More useful is this linear kernel. It's a constant plus a dot product, so this is a dot product kernel, clearly. And this then relates to a linear function priors. So you can see those functions that you can draw from the Gaussian process down here. They are all linear. So you can also, if I jump to that point directly, use this for Bayesian linear modeling. You can look at that other slide set too. For now, we'll just try to understand the relation between these functions here on the left-hand side and this thing here on the right-hand side. So what you see here on the right-hand side is a covariance matrix of 25 sampled points. So we just sampled points on the x-axis, 25. And so the first point here is -2, -2. This grows here until 2, and this also grows until 2, of course. So down here we are at the point where the correlation of this point with itself at 2. So what this means is that if I have some point, let's say -2, that of course the correlation with itself is rather high, and it always should be, but it is smaller, it decreases as we go to the right hand side. So if we say we want to see the correlation between this point x1 and that point x2, and if we say x1 is -2 and x2 is 2, then this here exactly is the covariance of these 2 points. Okay, we don't see the numbers here, but it's also not the most important point here. But we see that the further we go away, the smaller the correlation is, okay? And it even gets smaller behind that. In the end, it's even negative. So we have a perfect negative correlation, which means in this case that if we don't have an intercept term, so let's say theta 0 is 0, and I know that one point here, what can happen? I already know the line has to go through the origin, 0, 0. So I can perfectly already know that line here. There's no uncertainty anymore. And of course, this point and that point are perfectly negative correlated. Of course, are not the points correlated. That's abuse of, I don't know, of speech here, but there are random variables lying under these points. Okay, so we measure directional similarity. I think that this should be clear now. And this is not a stationary kernel. Why not? If you look at this graphic again, you have to switch to rotate this thing by 90 degrees compared with what we have seen on the other slides, because we are starting with -2, -2 here and go to 2, 2 there, okay? But other than that, the same thing holds. So if it would be a stationary kernel, then all these lines should be parallel, which they are not, clearly. Okay, but later we'll see stationary kernels as well. Okay, a slight generalization of the linear kernel is the polynomial kernel. So we do the same thing, but well, take it to the power of p. Then we no longer have linear function priors, but polynomial function priors. And this, of course, allows for nonlinearity through the higher order monomials and the interaction terms. And you see here 3 examples. Degree 1 is the linear form from before. Degree 2 are parabolas, and degree 5 are, well, more flexible polynomials. And you see here the covariance matrix for the degree 2 And if you go through this quickly in your mind, eyeballing, if you understand this, then maybe you will see that if I have one point here and there, that's -2 and +2. Sorry, so let's really just look at this correlation here. This is a very high positive correlation, which makes sense, because if I know this point here, that point should more or less have the same value, right? And if we don't have an intercept, it even has to be the exact same value if these functions go through the origin. But if they don't go through the origin, it doesn't have to be the same point, but they are still highly correlated, and the points at -2 and 0 are not that highly correlated, right? Okay, moving on to some other kernel functions now. We are looking at the squared exponential kernel, which you might have seen some slides before already in this other example. We have already seen that this is a stationary covariance function, which you can see here again. So if I draw these contour lines here, they are parallel to each other, right? And you can also see it in the formula because it's a function of the difference of x and x tilde, right? It's also called Gaussian kernel or radial basis function, and it's a continuous and very differentiable functions that we get here, and the covariance decays rather quickly in distance. So this means if the distance grows, or if 2 points grow further away from each other, they are less and less correlated, which, well, makes sense. It's this spatial correlation pattern again. And this function has a parameter, this parameter L, which is called length scale or characteristic length scale, and 3 examples for this length scale here, 0.1, 1.0 and 10.0. And you can see that for small length scale values, the functions are rather wiggly, and for larger length scale values, they become rather smooth. Okay, so you can control the smoothness of the function through this characteristic length scale. We'll speak about this a bit more in detail later, but let's have a quick check if we understand that this goes in the correct direction. So what happens if L goes up? Then 1 divided by L goes down, minus 1 divided by L goes up, which means that points at a certain distance are rather highly correlated, right? So, and if they are highly correlated, it's a rather smooth function, okay? Because nothing very much can happen between these 2 points. The exponential kernel looks similar to the squared exponential kernel, of course. Is the difference only that we do not have a square here. And this turns the function or the functions that we draw from a Gaussian process into continuous functions, but not differentiable functions anymore. So we can model functions with abrupt variations if we want to do that. The covariance decays exponentially with the distance, and we also have some characteristic length scale which governs the wiggliness or the smoothness. And also here, small length scale means wiggly functions. Large length scale means smoother functions, but in this case all of them are non-differentiable. It's also a stationary kernel, what you can see here, because all these things are parallel to each other. The Matérn kernel is a generalization of both the exponential and the squared exponential kernel. So the formula, I will not read it out here, is perhaps rather long, but with the smoothness parameter nu, you can directly get the squared exponential or the exponential kernel if you want to. We also have a length scale here, which also governs the smoothness, but we have a second smoothness parameter, which is the nu, the smoothness parameter nu. It is stationary and isotropic. If you think back to squared exponential and exponential, they were also isotropic because they were just depending on the length of the difference, right? So on the distance. And you see some examples here for the Matérn kernel for different values of the smoothness parameter nu. A totally different form of kernel is this periodic kernel. It's called, or there are many different periodic kernels, and one of these periodic kernels is the radial periodic kernel. The radial already implies some kind of isotropy, right? Because we have rotation invariance here. But it has another very interesting property, which is the periodicity, of course. So if you look at the functions down here that we draw from this, maybe we can best see it here for a period of 2. So if we have a difference of 2 here in x space, then we have exactly the same point, okay? So for a given function from this Gaussian process, or every function drawn from this Gaussian process with that radial periodic kernel is perfectly periodic, and the period is governed by m. So here in that case, m is 2, and you can see the periodicity, I think, with the sine function here. Of course, the sine function per se is periodic, so everything you do with this will be periodic too. M governs the period, and we also have a length scale L, which governs the smoothness between the period points, let's say. It's also stationary. We can have, or we do have, parallel contour lines here, and it's also isotropic because it's only dependent on the distance here. Yes. And it works also, of course, in more dimensions than just in one. And in 2 dimensions, you can imagine when you throw a stone into water, then you have these waves, and they go in the different directions at the same pace, right? So if you don't have any other circumstances, just these waves will be circles. An alternative to this radial periodic kernel would be a product of 1D periodic kernels, where we don't divide everything for all these dimensions by L square, but where we have maybe different periods here, right? We could also have different length scales or just different length scales, so you can do whatever you want basically. But the difference is then that this may have different periods in different dimensions. So if we are with a stone in the water again, then this would mean that the waves wouldn't be circles anymore, but they would be ellipses, right? So maybe something like this. Okay, and one last example of a covariance function, a very different approach here, is the Brownian motion, where we have the minimum of xj and x tilde j, and if we have more than one dimension in the feature space, then the product on these. And then we get, well, this Brownian motion. In physics, this is used a lot for random fluctuations of particles. With this definition, we would say that the dimensions are independent from each other, right? Because we are just having the product here, so no dependence between the dimensions. And if we have a non-1D input, then it's also called a Brownian sheet. Okay, and the last point for this video is, or are some more comments on the characteristic length scale. Let's start with an isotropic kernel. We already said we can write the isotropic kernel as a function of the distance. Okay, this could be the squared exponential function, for example. We can write this squared exponential function as this thing here, right? We can also just divide r by L and then take the square of this. And of course, as we have seen before, the length scale governs the wiggliness of this function. So if we have a high L, we have smooth functions, something like this. And if we have a low characteristic length scale, we have rather wiggly functions. In support vector machines, this is also called bandwidth or kernel width or inverse kernel width, but everything should mean the same. Okay. That was a characteristic length scale for the isotropic case. Now we can look at stationary kernels again. And what we want to do now, as I told you in the radial periodic kernel, where we had different periods then for different dimensions, also we can have different distance components, or we can modulate every distance component by an individual length scale, LG. So, of course, if we have an isotropic kernel, we can also write it as a stationary kernel, where we don't directly write it as function of r, but function of d. And if we do this, we can also just put a 1 divided by Lj before each distance component, right? So that we modulate each unique distance component by a different length scale. Okay, this is then the product of 1D kernels, one for each input dimension, and the correlation in each dimension is then described by these 1D kernels, and its distance component is modulated by this Lj. Why is this maybe a good idea? So we have these p different characteristic length scales now for p dimensions in the feature space, and the intuition for the length scale is how far do we have to move along this one axis to become uncorrelated. And if L is very long, very large, then we have to move very far away to become uncorrelated. Right? So we could use this to determine the importance of a feature. Why is that? Yeah, because if we have a very large L, then the covariance effectively is independent of the ith feature, so this feature maybe isn't that important at all, right? Because changes in this feature, or small changes in this feature, don't really do anything to the output, right? Because the length scale is so long. And we can also use this for some automatic rescaling if we estimate the length scales. This is possible. Of course, if we have a lot of length scales to estimate, this gets hard at some point computationally, but it's doable. Okay, so now we had characteristic length scales for each dimension, and we can of course say, well, just write this down. So the Euclidean norm is just some squared form, right? So we can generalize the principle even more. So we can plug something between dt and d to generalize this even more. So here we plugged in some matrix M, which we just squeeze between dt and d. And if this matrix is just the identity matrix multiplied by a constant factor, then this is just the vanilla form. We are modulating all the dimensions with the same characteristic length scale. If for M2 we use a diagonal matrix where the values on the diagonal could be different, then we have the last version with different characteristic length scales. So, but still each dimension is modulated independently from the other, but each dimension has its own characteristic length scale. But we can even generalize this further by saying, okay, now the weight matrix M3 can be some gamma t matrix product plus some diagonal matrix, and this then corresponds to a rotation of the feature space. You can see this better, I guess, with these visualizations here. So if on the left hand side, that's the vanilla case, we have the same variation in all directions. The second case is we have different variations in the different dimensions, right? So if I go in that direction, it's rather wiggly, right? So in the x1 direction. But if I go in x2 direction, well, not that much happens, right? So we have less variation in the x2 direction than in the x1 direction. But then in the third and last case, it's even perhaps a bit weird on first glance. But what happens here is that this gamma t determines some rotation, and then we have a lot of variation in the direction of the main axis of this matrix here, of this rotation matrix. And yeah, this can also be estimated, of course, which doesn't make things easier, but it's also doable. And in some situations, this may be also a very good idea, but this depends a lot on your use case, of course.